Let's try to get some intuition about Green's theorem. Let C be a positively oriented, piecewise smooth, simple, closed curve in the plane. Let F be a vector field such that the component functions P and Q have continuous partial derivatives on an open region that contains D, the region bounded by C. Then, the line integral of F is equal to the integral over the region D of the function Q partial with respect to X minus P partial with respect to Y dA. Positively oriented means that the curve is oriented counterclockwise, such that if you imagine yourself walking along the curve, the interior region is on your left as you walk around. Piecewise smooth means finitely many cusps. So it's smooth apart from finitely many points that it could have. It's simple, meaning it doesn't have any self-intersections. It's closed, meaning it doesn't go from here to here. It loops back around to where it started. And the component functions P and Q should have continuous partial derivatives on an open region that contains D, the region bounded by C. That means that these partials have to be continuous on a region that's a little bit bigger than C. Then this line integral equals the integral over all of D of this function. Let's try to understand why that's true. The first thing we'll need is some intuition about two-dimensional curl. So again, let F be a vector field with component functions P and Q. And imagine that this is a circle centered right here, fixed in the plane. And now suppose that we have a vector field that is growing larger as x increases. So the vector field is pushing harder on this side of the circle, the imaginary circle, than it is on this side, which tends to cause a rotation in the positive direction. Consider instead, imagine if our vector field is increasing as y increases. So in this case, the vector field is pushing harder on this part of the circle, so it's inducing a negative rotation in the clockwise direction. If we integrate over the curve to measure the amount that the vector field is causing it to rotate, that is the line integral over the curve. And then in the definition of curl, we divide this by the area of the circle. So we have the line integral divided by the area of this circle, and then we take the limit as that area goes to 0 of the sort of average turning power over this whole thing. So tiny, 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 it's shrinking to a point. And it takes some proving, but when you take this limit, it comes out to the partial of Q with respect to X minus the partial of P with respect to Y. So this is not obvious. This takes some proving. But we can get some intuition about why this expression is reasonable for measuring the turning power of the vector field at a point. Take a look at the vector field that's inducing this positive rotation. The vector field is increasing in magnitude in the vertical direction as x increases. Q gives the vertical component, so if the change in Q with respect to x is positive, we would expect a positive rotation. And now consider this term, the partial of P with respect to Y. So P gives the horizontal motion, and in this vector field, the magnitude of the vector field is increasing in the x direction as y increases, which is tending to induce a negative rotation. So if this term is larger, we get a negative rotation, and if this term is larger, we get a positive rotation. The next idea we need is cancellation of line integrals. The idea is this. if you were to integrate a vector field along this curve in this direction, and then integrate the line integral again, but with the opposite orientation, and then add the two results, then you'll get 0. And that's because the integral from a to b, f of t dt, is equal to negative the integral from b to a, f of t dt. A running theme, reversing orientation, gives you a negative result. So if we add this to both sides, we get the integral from a to b of f dt plus the integral from b to a, f dt equals 0. Let's apply this to a closed curve C. So here's a closed curve with positive orientation. We can integrate vector field around this curve. But what I want to do is subdivide this region so that we get two curves. Call this one C1 and C2. Now, in order to keep it with positive orientation, C1 has to have this orientation, and C2 has to have this orientation, so that the integral over the whole thing is equal to the integral around C1, f dot dr, plus the integral around C2 of the vector field. But then if you do both of these integrals, that will include integrating across this line once in this direction and once in this direction. So that will cancel out. And you can get the integral around the outer circle C by integrating over the two inner regions. What if we subdivide into 4 regions around the positively oriented curve C? So in order to keep the curves positively oriented, we're integrating around this way for, let's call this C1, and then C2 down here must have this orientation in order for the orientation to be positive. And if this is C3, then for this to have positive orientation, we have to integrate in this direction. And then if we call this C4, then in order for this to have positive orientation, it has to be going this way, that way, that way. So across each of these pieces of curve that are not in our original curve C, we have an integral in both directions, which will then cancel out, so that the integral over C of the vector field, the line integral, is going to be the sum, I goes from 1 to 4, of the integral around Ci of the vector field. We can iterate this process and divide the region inside the curve into many, many small zones. And in each of these little zones, the orientation is positive, so that at every iterative step, this sum of the integrals over all of these zones will still be equal to the original line integral around C. All right, and what happens when we take this limit of more and more smaller and smaller sums? It turns into the integral. So this will be the integral over the inner region D, D is the interior, of, well, what's being measured in these little spots. As these get tinier and tinier, and they approach a pointwise function that describes the curl at every point. Which, as earlier, we described that the curl of f is given by this scalar function, the partial of q with respect to x minus the partial of p with respect to y. And that's for a vector field f with the x component p and y component q.